Hello everyone, welcome to Sunya IAS and welcome to this lecture series of modern algebra and which is asked in your paper 2 section A. In the last lecture, we did some of the basics of groups, and before that we saw what are sets, what are relations, functions, and then we moved on to binary operations, and then finally we saw the basic definition of groups, right? So from today, we'll be starting with groups, the proper definition, and some theorems related to it, and also some questions, okay? So we know what is a monoid. A monoid is a algebraic structure which has a non-empty set and a binary operation, and it satisfies some postulates. That is, आपका सबसे पहले closure property, then it has associativity, and it has existence of identity. So when this monoid structure has the existence of inverse, it forms a group, right? अब थोड़ा सा पेन चलाएंगे, सुनना नहीं है बस. So we'll be using our pens now and we'll be writing the proper definition bit by bit for every postulate, for every property. What happens is that when we are studying modern algebra, when we think about it, हाँ ठीक है, inverse हो गया, identity हो गया, but when it comes to writing down on paper, it becomes very difficult. So it's very important for you to develop the habit right from the start of writing whatever you are thinking in modern algebra. Clear? Okay. So you can pause the video and write the definition by yourself and then check, or you can follow along. Clear? What is a group? An algebraic structure a non-empty set G paired with a binary operation forms a group if it satisfies the following postulate. Now, let A, B belong to the non-empty set G. Alright. Now the first property is your closure property. A, B, C are elements of the non-empty set G that we have taken. Now, A star B always should belong to G, and this should be true for all A comma B belongs to. Then we can say that star is closed, or you should say, just write, satisfies closure property, right? Now second, we have associativity. What is associativity? That it does not matter that in what order I am applying the binary operation, the answer should always be the same. That means for this equation, LHS should always be equal to RHS, and this should be true for all A, B, C belongs to. Clear? Now third, we have existence of identity for every, या फिर, right, there exists E belongs to G for all A belongs to G, such that A operation E equals to E operation A equals to, and this E is known as your identity operation. Clear? All right. Now finally, we have fourth number, we have existence of inverse. Now for all A belongs to G, there exists A inverse belongs to G such that A operation A inverse equals to A inverse operation A equals to E. And what is E? Your identity element. Here, then G dot or I should say star. We are just assuming the binary operation to be star. So G star forms a clear? All right. So with the binary operation forms a group. Wait, na? Just mention the operation here. Okay. Now that we know what is the proper definition, this is okay, this is fine. Finite, the groups which have finite number of elements are known as finite groups, right? And which have infinite number of elements are known as infinite groups. And the order of elements, order of groups depends on the number of elements. Clear? So for a finite group, the order is always finite. And for an infinite group, the order is always going to be infinite, right? Abhi infinite and finite mein abhi hum nahi jayenge, because that is of not that much use here, right? Chalo, let's take up this question. Check the following if it forms a group with respect to the binary operation star on them as follows. So we are given that we are supposed to check for set of integers, rational numbers and real numbers with respect to addition. Clear? Chalo, pick up your pens and start. Now first let's check, let G star be set of integers with addition. First is your closure property. Now A plus B, or let's mention first that let A comma B belongs to integers. So both of them are going to be integers. Now A plus B equals to C, which belongs to Z. Why? Because addition of, or we'll just write integer value, right? When you add any two integers, the result is always going to be an integer only. The problem with natural numbers was when we were using negative sign, that means subtraction when we were using, so we were getting negative numbers which were not part of the set. Okay, so that problem is not going to be here. Now, okay, next up we have associativity. Now, A plus B plus C equals to A plus B plus C. You can take any two examples also. 1, 2 and 3 I'll take here, and 1 plus 2 plus 3. So order does not matter in which I will be solving or applying the operation here. So this will be 1 plus 5, 1 plus 5, and this will be 3 plus 3, and this will give me 6 equals to 6. That means this will be true for all ABC that are integers, right? Chalo. Next up we have existence of identity. What is existence of identity? What is an identity element? Let A belongs to the set of integers and I need E such that E operation A equals to A operation E equals to A. I can think of only one such number which is going to give me this result, that is 0 plus a equals to a plus 0 equals to a. So that means, what is my identity element here? Identity element is 0, and then you have your existence of inverse. What is the definition of inverse? That for all a belongs to Z, there must exist a inverse belongs to G, such that a plus a inverse equals to a inverse plus a equals to the identity element, that is 0. So if a plus a inverse equals to 0, this implies that a inverse is nothing but minus of a, and which is a valid value. So for each a, you are going to have an inverse that is going to be minus of a, right? So this is true for all a belongs to. Clear? So this implies that Z, that is the set of integers along with addition, forms a group, right? And now you will be taking up homework. Similarly, prove that real numbers along with addition and rational numbers along with addition, right? And be very clear about the steps that you are writing. Okay, what is given, what you are supposed to assume, and what you are going to think about कि कौन सा element है, किस type का element है. So be very careful about it, right? So these two you will do. Similarly, we can prove them. Chalo. Then we have set of integers, rational numbers and real numbers with respect to multiplication. Now let's take rational numbers set here. Okay, so let's say we have let g dot b or g star b q dot, right? Now first is your closure property. Now let a comma b be rational numbers. Now a dot b is always going to be a rational number only, right? So the multiplication is going to be, the result of a dot b is always going to be a rational number only. So this implies that closure property is satisfied, right? Now similarly, we can say that it will follow associativity as well, right? So let a comma b comma c belong to rational numbers and a dot b dot c equals to a dot b dot c. So यहाँ पे you can take any example and then you can prove, and it is going to follow. So for all, or I should write it here, for all a comma b comma c belongs to associative property satisfied. Existence of identity. So there exist, or I should say, for all a belongs to q, there exist e, there must exist, or I should write, let's say पहले देख लेते हैं what is the property. So a star equals to e star a equals to a, right? Now I need a number which when operated with a is going to give me a again. Multiplication mein what is that number? That is 1. What is the value of e here? E is going to be 1. Then finally we have existence of inverse. Now for all a belongs to q, that is rational number, a inverse belongs to q, that is a dot a inverse equals to a inverse dot a equals to e. What is that? One. So this implies that a equals to a inverse equals to 1 by a, right? So this is true for all a belongs to, right? Now, or you can write it in language form also, that for all a there must exist a inverse that belongs to q such that this property is being satisfied, right? So you can see that for all elements that this is going to satisfy, right? Now all of the people who just followed along with this proof that we were doing missed one point, and यही गलती हो जाती है when we are doing some basic, very basic questions, when it comes to some complex questions. यहाँ पे तो straight आपका set दिया हुआ है, right? The problem with this part here is that if I take a equals to 0, is a inverse going to be a valid value? No. So clearly we can say that the set of rational numbers along with multiplication, it does not form a group, right? Similar is going to be the case with integers, and similar is going to be the case with real numbers. So how do they form groups? That we'll be taking up later on, but for now we know that set of integers, set of rational numbers, and your set of real numbers, they form groups with respect to real numbers, but they do not form groups with respect to multiplication. Okay, chalo, moving on, we have the set of all positive irrational numbers under multiplication. अब क्या चेक करना है आपको? G is there, G star has been defined to us as irrational numbers with multiplication. अब जब भी when you feel that a certain group or a certain set is not going to form a group, you look for examples with which you can fail any one of the property, right? First thing I can think of is let a equals to root 2. So if a is equals to root 2, then I will be checking the closure property. Root 2 multiplied by root 2 is going to be what? 2. Similarly, root 3 into root 3 is going to be 3. Root 5 into root 5 is again going to be 5. And all of these numbers are not rational numbers. They do not belong to rational numbers, right? That means the set of irrational numbers under multiplication is not closed only. है ना, पहली ही property में it is failing. That means आपका irrational number does not form a group with respect to multiplication. Clear? चलो. Next, now we have set of all 2 cross 2 matrices over integers under matrix addition. Over integers. So आपको matrices की entries कहाँ से लेनी है? Integers से, and the operation given to us is matrix addition. Clear? चलो, pick up your pens. First one is closure property. Let a comma b, to define the set as well first, na? Let the set be G, a equals to aij cross 2, and aij we are taking from integer. Here, okay. So let A and B belongs to G. Now A plus B is going to look like A11, A12, A21, A22 plus B11, B12, B21, B22. So when we are adding the two matrices, respective terms are added. That means iska first term and iska first term is going to be added. So A11 plus B11, then A12 plus B12, then A21 plus B21, and finally A22 plus B22. And we can clearly see that all of these are integers only. So addition of these numbers are always going to be integers. So if I call this set as C, this is also going to belong to the group G, or the set G, that is the set of all 2 cross 2 matrices where the entries are being taken from the set of integers. Clear? Now associativity. Let A comma B comma C belongs to G, and A plus B plus C equals to A plus B plus, right? Now eventually what you are doing, eventually आप क्या कर रहे हो, आप addition ही तो कर रहे हो elements का, right? And हमें पता है that addition is associative. So base operation is associative. That means base operation is addition. That means the matrix addition is also going to be associative in nature. आपको करना है, if you want आप लिख के कर सकते हो. You can assume all of the values for A, B, C, and then you can add up and then write it in a nice, laid out form. Clear? So here I can say that this implies that underlying operation is addition, or we can say component wise addition. So this implies that G satisfies associativity. All right, then we have existence of inverse or identity. Now for A belongs to B, there exists A plus some matrix, or I should say 0 matrix, such that I'm going to get the answer as A only, right? So what is the identity element here? The identity element here is nothing but the 0 matrix of 2 cross 2 order, or we can write it now. Similarly we can write existence of inverse. Now for A belongs to G, there exists minus of A belongs to G, such that A plus minus of A equals to minus of A plus A equals to identity matrix, that is your 0 matrix, right? So for all A belongs to G, there exists minus A belongs to G, and minus A is going to be the inverse of the matrix that we are talking about, that is an element of the G. Clear? So we can say that the set of all 2 cross 2 matrices over integers under matrix addition forms a group, right? Now definitely अब हमने addition के बारे में बात करी है, so we will be talking about the multiplication as well, right? So set of all 2 cross 2 matrices over integers under matrix multiplication. So now pay attention, it is given to us as matrix multiplication, not component wise multiplication. Clear? Chalo. First one, the set, we can write the set here first. So G equals to A Aij cross 2, Aij belongs to integer, right? Now first one is your closure property. Now let A comma B belongs to G. A dot B is also going to belong to G only. The product of two integers is always going to be integers only. And then अगर आप component wise नहीं कर रहे हो, but you are doing the matrix multiplication, the ordinary multiplication that is done, then also you are going to get, आप एक करके देख लो example के लिए फटाफट से, A11, A12, A21, A22, then you have B11, B12, B21, B22. अब ये देखो, what do you do? आप पहले पूरा रो multiplied by this column, right? Then you add that to this row multiplication with this multiplication, right? Oh, sorry. You multiply the consecutive numbers here. First row, first column, consecutive numbers are multiplied and then added. That means A11 into B11 plus A12 plus into B21, right? So this is going to eventually give you an integer only, right? So first element is going to look like A11 B11 plus A21 A12 B21, right? So this is eventually going to give you integers. So we can say that all the elements that we are going to get in the multiplication of two matrices, which we have taken from the set G, is going to eventually fall back into the same set only, right? So closure property will be satisfied. So this implies that closure property is satisfied. अब यहाँ पे आता है एक छोटा सा मेहनत का काम that you will be doing. Why? Because you are going to assume three matrices and the elements of those three matrices as A11, A12, A21 and A22, and similarly for B and C. And then you are going to check if the associativity holds for matrix multiplication or not. Okay. For now, I will be saying that let A, B, C belongs to B and A dot B dot C equals to A dot B dot matrix multiplication is associative. Okay. तो यहाँ पे take it as a homework. साइड में थोड़ी मेहनत करनी पड़ेगी so that it gets etched into your memory. All right. So now we will be taking up the inverse part, right? Inverse and the identity part, right? Chalo. So what is identity with respect to matrix multiplication? That is your identity matrix. So 2 cross 2 mein the diagonal elements are 1, that is known as your identity element. So A dot I equals to I dot A equals to A. This implies that for all A belongs to B, there exist I belongs to G such that A operation E equals to E operation A, right? Now, finally, we have the inverse part. Now for inverse, we know what is the formula for multiplication. Matrix multiplication में क्या करना होता है? सबसे पहले you are supposed to calculate the determinant. What is determinant? AD minus B, where A is of the form A, B. Clear? Diagonally opposite elements को multiply करके you are taking the difference. That is what is happening. AD minus BC. So that is your determinant, right? Now what does A inverse look like? A inverse looks like 1 upon determinant of A. Then you take adjoint of A. That is nothing but आप ठीक है, we can write the value for it. That is going to be D, C, A and B with negative sign here and iska transpose. So this is going to be 1 upon dA D minus C then minus B on A, right? So this is your inverse, but there is a problem. What is the problem? We are talking about the set of all 2 cross 2 matrices over integers under matrix multiplication. What if for some element that belongs to G, the determinant comes out to be 0? Right? It can happen ना. आप कोई भी एक constant ले लो, A. So this is going to give you determinant as 0, A square minus A square, right? So for those kind of elements, that is for those kind of matrices, the inverse is not going to exist, right? So आपका यहाँ तक तो सब sorted है, but the problem is when we are talking about existence of inverse. So when it comes to the set of all 2 cross 2 matrices over integers under matrix multiplication, it does not form a group. What kind of set forms a group, that we will be seeing later on. Clear? चलो अभी यहाँ पे we are just understanding how किस तरीके से आप figure out कर सकते हो कि where the group is going to or the set is going to fail or the algebraic structure is going to fail to become a group, right? चलो next up we have, I guess one more question is there. Yeah. So we have a set G where the elements are of the form 2 to the power R and R is 0, 1, 2, 3 and minus 1, minus 2, minus 3. That means basically R belongs to integers, right? And the elements are of the form 2 raised to the power R. So what is G going to look like? 2 raised to the power 0, then 2 raised to the power plus minus 1, 2 raised to the power plus minus 2, then 2 raised to the power plus minus 3. And what are these elements? This is 1, this is comma 1 by 2, this is 4 comma 1 by 4, then you have 8 comma 1 by, right? So these are the elements of the set. Now we know how the set is going to look like. क्या होता है जब आपको इस तरीके की नोटेशन दे दी जाती है तो इट बिकम्स अ बिट कंफ्यूजिंग टू विजुअलाइज द एलिमेंट्स ऑफ द सेट, राइट? तो आप क्या कर सकते हो, साइड में आप एक मार्जिन बना के यू कैन राइट द एलिमेंट्स ऑफ द सेट सो दैट इट बिकम्स ईजियर फॉर यू टू विजुअलाइज, राइट? चलो now we'll be taking up the proof or we'll just check that if it is forming a group or not. So G star is given to us as, the group is G only and this is multiplication, right? Now first one is your closure property. So 2, or I should say let R1 comma R2 belong to Z. Now 2R1 dot 2R2 are going to be the two elements of the set, right? Clear? Any problem? Now, this can be written as 2 raised to the power r1 plus r2, right? Now, if this is an integer, what is their sum going to be? The sum is always going to be an integer, and it is obviously going to lie in the set, right? So this definitely belongs to. So closure property is satisfied. Now, what about associativity? R2 and R3 belong to integers, and 2 raised to the power r1 raised to the power r2 and 2 raised to the power r3 belongs to, right? Now 2 r1 dot r2 dot r3 . So if I solve this bracket first, it is going to give me 2 r1 plus r2, right, dot 2 r3, and here if I'm solving this bracket first, I'll get 2 r1 dot 2 r2 plus r3, right? And then if I solve the remaining ones, I'm going to get 2 r1 plus r2 plus r3. This is 2 raised to the power r1 plus r2 plus r3, which are nothing but equal. So it does not matter in which order you are solving them, you are always going to get the same answer. Yeah. Chalo. Next. Existence of identity. Now let 2 raised to the power r belongs to, let this be an element, right? Now I need an element 2 raised to the power r dot e equals to e dot 2 raised to the power r, such that I get 2 raised to the power r back. So which is nothing but e equals to 1, which in terms of this group is going to be 2 raised to the power 0. So technically the identity element is going to be 2 raised to the power 0. And then we have inverse. So I can write there exists e equals to 2 raised to the power 0 belongs to G, such that a dot e equals to e dot a. Now let 2 raised to the power r belongs to G. Now I need an element such that the element is going to be of the form this only, right? Or I should write it as dash, r dash. Clear? Whatever the element is going to be, it is going to belong to G, so that it is going to be of the form 2 raised to the power r dash, or ठीक है, symbol के लिए let's just take a inverse. ठीक है, it will be relatively easier to write. So we need such that it is equal to e, that is nothing but 2 raised to the power 0. So 2 raised to the power r dot a inverse equals to 1. So a inverse is going to be nothing but 1 upon 2 raised to the power r, which is nothing but 2 raised to the power minus r, right? So here we can see that for every r there is a minus r, है ना, चाहे वो नेगेटिव है तो पॉजिटिव r हो जाएगा उसके लिए. So that means for every element I am going to get an inverse element, and this is going to be true for all 2 raised to the power r, that belongs to G. Okay, so a inverse is going to be 2 raised to the power minus r. Yeah, so this implies that G, the set G with under multiplication forms a, yeah, चलो. Now ये तो हो गए आपके जनरल सेंस के आपके कुछ what I would call सेट्स जिन पे आपको पता है कि व्हाट इज द बाइनरी ऑपरेशन एंड हाउ डू वी अप्लाई इट. मतलब एडिशन, मल्टीप्लिकेशन, मैट्रिक्स मल्टीप्लिकेशन, दीज आर some things which we are very familiar with, right? बट वेन यू सी सम डिफरेंट काइंड ऑफ बाइनरी ऑपरेशन, है ना, एकदम से वो दिमाग में स्ट्राइक नहीं करता. व्हाट हैपेंस इज, जब आप ये मेहनत नहीं करते हो, ये वाली मेहनत नहीं करते हो, आपको अभी लग रहा होगा कि वाई आर वी डूइंग सो बेसिक, मतलब सच बेसिक थिंग्स, राइट. जब आप ये चीज़ नहीं करते हो, व्हाट यू आर सपोज टू राइट लाइक टू द वेरी स्मॉलेस्ट एलिमेंट, इफ यू आर नॉट डूइंग दैट, प्रॉब्लम क्या होती है, व्हेन यू आर डूइंग सच काइंड ऑफ क्वेश्चंस, वहाँ पे गलती हो जाती है और आपका इन्वर्स की वैल्यू या फिर आपकी आइडेंटिटी की वैल्यू गलत आ जाती है. और वहाँ पे क्या होता है, एकदम से इतना दिमाग नहीं चलता कि हम उसको वेरीफाई करके भी देख लें, राइट. चलो, check if the following form group with respect to the binary operation star on them as follows. So we are given the set Z, that is the set of integers with a star b, and the operation is a plus b plus 1. Clear? I guess this is very easy. Why? Because आपका eventually कर तो आप addition ही रहे हो, you are just adding one constant number, that is 1. Clear? So फटाफट से देखते हैं how we are going to solve them. So operation has been given to us as now first one is your closure. Now if a comma b are integers, so most definitely a plus b plus 1 is always going to be an integer as well, right. आपका ये अगर 2 है, this is 3, तो 2 plus 3 is 5, 5 plus 1 is going to be 6. ऐसा तो नहीं होगा ना कि आपका 2 plus 3 करा and then add 1 करके you are getting some upon number, 1 upon something number, that is not going to be an integer, right. So most definitely if you are just adding 1 in any of the integers, you are again going to get an integer. So closure property is satisfied. Now associativity. A comma b comma c belongs to integers. Now a operation b operation c equals to a operation b. Now a operation b is going to be what? A plus b plus 1. Now pay attention, this is one whole element here. Now operation c is going to be a operation b plus c plus 1 here. Now what you are supposed to do is you are supposed to add these two integers and add one more. So a plus b plus 1 plus c plus 1, a plus b plus c plus 1 plus 1. So this is nothing but a plus b plus c plus 2 equals to a plus b plus c plus 1, which gives us that this is true for all a, b, c belongs to integers, hence associative property is satisfied, right. Now third one is your existence of identity. Now I need a star d, or I should say I'll take e only here, e, such that e star a is again equal to a. So this implies that a star e equals to a plus e plus 1, right, and which should be again equal to a, right. So can I find the value of e from here? So a plus e plus 1 equals to a. So e is going to be nothing but minus 1. फटाफट से we can verify it as well. हैबिट में डाल लो इसको so that आगे जाके कभी प्रॉब्लम ना हो आपको. तो a when operated with minus 1, what you are going to do? a plus minus 1 plus 1. So you'll get eventually a. So that means minus 1 is going to be the identity element for this group. And we know that it belongs to the set of integers, right? Now fourth number pe we have existence of inverse. I need a value a inverse such that I get the identity element here. And what is that? -1, right? So A star, A inverse is going to be what? A plus A inverse plus 1, and this has to be equal to 1. So for this to be true, what is going to be the value of A inverse? It is going to be -1 minus 1 minus of A. This is -2 minus A. What is the value of A inverse? -2 minus A. आप इसको verify करके भी देख सकते हो. So A operation A inverse -2 minus A will be what? A plus B plus 1. So this is A plus -2 minus A plus 1. So this is A -2 minus A plus 1, and A and A are going to get cancelled, and you'll be left with -1, which is nothing but your identity element, right? So clearly we can see that the set Z with the binary operation A star B, A plus B plus 1 is a group. It does form a group where for all elements identity element exists, and for all elements the inverse exists, right? Now why are we doing such kind of questions? Because I guess either this one or the previous one, this question has been asked. It is one of your PYQs, right? So फटाफट से just pause the video and do this question as well. यहाँ पे क्या है? You are given the binary operation in terms of ordered pairs, right? So be very careful. Pause करो, solve करो, or you want to follow along, you can follow along. So what is the set? Set is the set G. It is the set of all ordered pairs where I am taking the first ordered pair from rational numbers, and B is also from rational numbers, and A is not equal to, right? Chalo. Let's see first about the closure property. All right. Now let A comma B comma C comma D belong to, right? ध्यान देना है that ordered pairs are the elements here. Clear? Now what is the operation? A comma B star C comma D. And how is the binary operation defined? पहले A C multiply करना है, then you are supposed to multiply A D and you have to add B, right? So A C A D plus B. Now if these two are rational numbers, the product of two rational numbers is again going to be a rational number only, right? And the product of two rational numbers plus a rational number is again going to be a rational number, right? So closure property is going to get satisfied. Why? Because both of the coordinates are going to belong to rational numbers only, right? So this implies that closure property is satisfied. Now let's check for associativity. Let A comma B, C comma D and E comma F belong to. Now we are supposed to check A operation A comma B operation C comma D operation E comma F, right? So this is going to be a lengthy one, so I'm first going to take the right hand side, then we'll take up the left hand side, right? So RHS will be A comma B operation C comma D operation E comma F. First we'll be solving A comma B. What is the ordered pair going to look like here? AC, that means C into E is going to be the first order pair. Then AD, that is CF plus D, right? Now apply the same with AB and CE, CF plus D. Now first you are supposed to multiply the first two ordered pairs. first two coordinates of the ordered pairs. So that is going to be A into C, that is A into CE. So ACE is going to be the first coordinate, and then A into D, right? A into D, yes. So A into CF plus D plus B, that is the second coordinate of the first ordered pair. So that is going to be B. So here we'll be left with what? ACE, comma, ACF plus AD plus B. Alright, chalo. Let's take up the left hand side. So A comma B, operation C comma D, operation comma F, and we are going to apply it to these two. So it will be relatively easy. क्या होगा? AC comma AD plus B, and then you have comma, right? Now AC into the first coordinate here, so ACE, then AC into F plus B, so this is AD plus B, right? Now these two are the final coordinates. Are they equal? ACE comma ACF plus AD plus B, ACF plus AD plus B. So LHS is equal to RHS, right? This implies that associativity is satisfied, right? Alright, let's take up identity now. Now for identity, what do I need? A comma B, operation E1 comma E2, and I need A comma B back, right? ठीक है, आप स्विच करके भी लिख लेना इसको, that's not a problem. यहाँ पे अभी main agenda is to find out the values of E1 and E2, right? चलो, so when we operate these two, what are the values going to be? AE comma AE1 comma AE2 plus B, right? And since these are ordered pairs, the respective coordinates are going to be equal, right? So this implies that AE1 equals to A and AE2 plus B equals to B. So what is the value of E1? E1 is going to be 1. And what is the value of E2? E2 is going to be, B and B will be cancelled, so it will be 0, right? So this gives us the value of E1 comma E2 to be 1 comma 0, right? तो आप यहाँ पे चेक भी कर लो, कोई दिक्कत नहीं है. A comma B, operation 1 comma 0. A into C, that is A into 1 and A into 0 plus B, right? So you will be left with A comma B. So clearly 1 comma 0 is the identity element for the given set, right? Now continuing, we will be taking up inverse. Now we need A comma B, operation A inverse B inverse equals to E1 E2, right? Now A inverse comma A B inverse plus B equals to, what is the value of this? 1 comma 0, right? This we have already found out. So since these are ordered pairs and they are equal, so respective coordinates are going to be equal. So this implies that A dash equals to 1. This implies that A dash is nothing but, not A dash, A inverse. A inverse is 1 upon A. and here we have AB inverse plus B equals to 0. So B inverse is going to be minus B upon A. So for any element A comma B that belongs to the set, the inverse of that element is going to be 1 upon A comma minus B upon A. आप चेक भी कर लेंगे यहाँ पे A comma B operation 1 upon A comma minus B upon A. This is A into 1 upon A. This is the first coordinate, and then you are supposed to multiply this by this. So A into minus B by A plus B. This is A into A, I mean A cancelled by A. This is 1, and here we'll have A and A will be cancelled, minus B plus B is going to be, which is nothing but E1 comma E, right? So for all the elements A comma B that belong to the given set, we have identity element, that is 1 comma 0, and then we have the inverse element, that is 1 upon A comma minus B upon A. Clear? So clearly the set G forms a group when defined, when we are given the binary operation to be AC comma AD plus B. All right, chalo, let's take up next question. Okay, the set Q minus 1. Q minus 1 means that we are considering the set of all rational numbers apart from the number 1, right? When Q is the set of rational numbers with operation defined by A star B equals to A plus B minus AB. Clear? Fatafat se chalo. Those who want to pause the video, they can pause the video, or you can follow along. Closure. Let A comma B belong to minus 1, right? Now A plus B or A star B equals to A plus B minus AB. This is an integer, rational number. This is a rational number, and product of two rational numbers is also going to be a rational number. So eventually all of them are going to belong to rational numbers only, right? So this is also going to belong to rational number. So this implies that A star B belongs to Q minus 1, right? So closure property is satisfied. Next, we have associativity. Let A comma B comma C minus 1. Then you have A star B star C equals to A star B star. Now A star, so B star C is going to be what? B plus C minus B, and then here you will have A plus B minus AB operation C, right? Now this will be A plus this whole value and minus the product of these two, right? This is going to be A plus B plus C minus BC minus A bracket B plus C minus B. Here this is nothing but A plus B plus C minus BC minus AB minus AC plus AB C. Now I'll take a different color pen so it is more visible. Okay, this is going to be A plus B plus minus AB plus C minus the product of these. So this is going to be CA minus CB minus plus AB. Here this is going to be A plus B plus C, if I am to follow this same order. A plus B plus C minus AB minus AC minus BC plus AB. So clearly LHS equals to RHS. That means the given operation is associate, right? Next, then we have existence of identity. Now A star E equals to E star A equals to A, right? Now what is A star E? A plus E minus AE equals to A. Now for this situation to follow, what is going to be the value of E? A plus E minus AE equals to A. A and A will get cancelled. E can be taken common here, and we'll be left with 1 minus A. Now the product of two numbers has to be 0, right? Here, then either one of them have to be 0 or both of them are 0. But the problem here is that A belongs to the set G, right? And what is the set G? That is rational numbers minus 1. That means the value of A cannot be 1. So if 1 minus A is going to be equal to 0, that means A is going to be 1, and which is not possible. So we can write, since A cannot be equal to 1, this implies that E is 0, right? अगर आप यहाँ पे वो 1 नहीं देता, right? अगर वो mention नहीं होता that the set we have taken is Q minus 1, then there would have been ambiguity as to what is going to be the वैसे तो आप वैल्यू उसमें से भी निकालते, ठीक है, तो E is equals to 0 है, आप 1 minus A को 0 नीचे लेके जाते तो भी 0 ही आ जाता, that's fine, ठीक है. चलो, let's see existence of inverse. Now we need A operation A inverse equals to A inverse operation A to, so A plus A inverse minus A inverse equals to 0. So we have to find out the value of A inverse from here. So A inverse common, 1 minus A equals to minus A. So A inverse equals to minus A upon 1 minus. So A inverse is going to be minus A upon 1 minus A, or you can write it as A upon A minus 1. Clear? No problem in that. Now we can verify it as well. A operation minus A upon 1 minus A is going to be A plus B. A minus A upon 1 minus A minus the product of these two, this is going to be plus A square upon 1 minus A. So if you take the LCM, you're going to get A, 1 minus A से multiply करेंगे, minus A square minus A plus A square. This is 1 minus A. Both of these will get cancelled, and the answer is equals to 0, which is nothing but your identity element. Clear? Now that we are done with the questions, let's take some theorems. Now what does this theorem say? If G is a group with binary operation star, then the left cancellation and the right cancellation laws follow or hold in G. What does this mean? That for all, or I should say, let A comma B comma C belongs to, then AB equals to AC implies that, wait a second, space, so that we'll have the enough space for proof. Now that is, let A comma B comma C belongs to, then if AB equals to AC, this implies that B equals. That means if I am operating by the same element from the left side on both the sides, that means the left hand side and the right hand side, that I can cancel the same value from both the sides. that is जब मैं left की बात कर रही हूँ, right? So I can say that B is equals to C, and this is going to be true for all A, B and C belongs to, right? And similarly, if BA equals to CA, this implies that B equals to, okay? And this is also true for all ABC belongs to. Now let's take the proof for it. Very simple proof. क्या करना है आपको? You want only B and only C on these sides, and you want to remove A here, right? Now since G is a group, that means A is an element of the group G. That means it will have inverse as well. So if I post multiply by A inverse on both sides, A inverse A is going to give me identity, and I'll be left with B is equal to, right? Now let A comma B comma C belongs to G. There exists A inverse belongs to G such that A inverse equals to A inverse A equals to E, right? Why? E is a group. So inverse will exist for every element. Now we are given that AB equals to AC multiplying by A inverse on both the sides. We will get A inverse A B equals to A inverse A C. This will be EB equals to EC, which is nothing but B equals to, right? So this is nothing but your left cancellation law. Right? Now let's do this for the other side. Given BA equals to CA, right? Multiplying by A inverse on both the sides. So I'll get, or I can write post multiplying, and here I can write pre multiplying. ठीक है? Pre मतलब पहले, ठीक है? Post मतलब बाद में. So this will give me A inverse equals to C A inverse. So BE equals to CE and B. Hence that if G is a group, then left cancellation law and right cancellation law are going to hold in the group G, right? Moving on, we have the next theorem is if G is a group with binary operation dot or star or whatever you want to call it, and A and B are elements of G, then the linear equations AX equals to B and YA equals to B have unique solutions X and Y in G. पहली बात तो नोटिस करने वाली चीज क्या है, that it is given that G is a group, right? So all the properties that a group follows with respect to the binary operation, that is going to follow. And then A and B are the elements, then AX equals to B and YA is equals to B have unique solution. तो हमें ये बताना है that they have solutions, तो मतलब उनके पास solutions तो है ही, we are supposed to prove that they have unique solutions as well, right? चलो, let's take up the proof. Let G be a group with binary operation dot, right? Now let A and B belong to the group G, right? Now first we'll take given before that Now since A and B are elements of G, that means A inverse and B inverse are both going to belong to G. Clear? Now AX is equals to B is given to us, right? Post multiplying or pre-multiplying actually. Pre-multiplying से मिल जाएगा हमें? Yes, pre-multiplying by A inverse. So I'll get A inverse A x equals to A inverse, right? Now which leaves me with EX equals to A inverse B and X equals to A inverse B, right? Now since A inverse is also part of G, right, and B is also a part of G, that means it belongs to G. This implies that X belongs to G as well, right? And now if I substitute this value into equation 1, substituting value of X in equation 1. Now why I'm doing this step? Right, eventually I have to prove that AX is equals to B for any AB which are elements of G. X is going to be a solution, and then I have to prove that X is going to be a unique solution of that, right? So pehle unique se pehle you are supposed to prove that it is going to be a solution. So that is why I have taken out a value of X in terms of A and B, and then I'm going to substitute in the given equation, and then it is going to satisfy, and we can say that X is going to be a solution of the given equation, right? So now A X, what is the value of X? Inverse B equals to B. Now A inverse, since it is a group, it is going to hold associativity as well. So पहले अगर मैं इन दोनों को operate कर रही हूँ, so it is going to be the same thing if I operate these two first. Now A inverse is going to be what? E, and which is going to give me. So here you can write associativity holds. Now it is very important for you to have a clear picture as to what is given in the theorem that you are proving, और क्या given है and what you are supposed to prove. ठीक है, अब यहाँ पे एकदम assume करके नहीं चलना है कुछ भी. आप बोलोगे कि that I have the value A x is equals to A inverse B, but you will have to prove it by writing. ठीक है, so this implies that x equals to A inverse B is a solution. Clear? Now now for uniqueness. Up, I want to prove that x is equals to A inverse B is a unique solution. Here, for that I will assume the exact opposite of it to be true. That is going to be that using contradiction, let x1, or I should say x1 equals to, what is the value of x? A inverse B, right? So let it be, or I should say let ax1 equals to B and ax2 equals to B, and x1 is not equal to x2. B, two solutions of Ax equal to, right? Now if Ax1 is equals to B and Ax2 is also equals to B, can I write Ax1 equals to Ax2, right? And now since left cancellation laws hold in a group, A and A is going to get cancelled out. So I'm going to be left with x1 equals to x2, and the reason is going to be left cancellation law, right? So our contradiction, our assumption is wrong. That means x1 and x2 are not two separate values, they are the same values, right? So this implies that Ax equals to B has unique solution, right? Similarly, we can prove that YA equals to B will have unique solution. Clear? तो जैसे हमने इसको प्रूव किया, सिमिलरली वी कैन प्रूव दैट हाउ YA is equals to B is going to have the solution. क्या करोगे आप पहले उसमें, ऐसे ही जैसे आपने यहाँ से x की वैल्यू निकाली, in a similar manner you are going to find out the value for y and then you are going to substitute in the original equation. यहाँ से आपको प्रूव हो जाएगा that y is going to be the solution and then uniqueness in the same way you can follow. वहाँ पे क्या होगा, right cancellation law is going to come. Clear? चलो next one is a non-empty set G together with the binary operation dot is a group if and only if A, B, C. So okay, this is आपका associativity. Okay. And then you have for any AB belongs to G, the equations AX is equals to B and YA is equals to B have solutions in. Now what is the theorem saying? The theorem is saying that एक non-empty set है, ठीक है, and उसमें there is a binary operation and then you have, अगर उसमें associativity hold हो रही है and if these two equations have unique solutions or just have solutions, then it is going to form a group. तो अब हमारे पास देखो, आपके पास associativity है, आपके पास closure है. Now what are you supposed to prove? You are just supposed to prove the existence of inverse and existence of identity. Identity prove हो जाएगी group के लिए and then existence of inverse for each of the elements. तो आप क्या कह सकते हो? Then that if these two conditions hold and if you are able to prove that there is inverse and identity, then it is going to form a group, right? So now what we'll do, we'll assume that let a second है ना, let equations 1 and 2 hold. Now what are the two equations? This is 1 and this is 2. Clear? Then we just have to prove the existence of identity and inverse to prove that is a group, right? Now if second is true, that means that let A comma B belongs to G, or I should say just I'll take A for now. Let's say A belongs to G, be an element, be any element. Now if these two equations have solution, is it going to be true that AX is equals to A is also going to have a solution, right? And similarly YA is equals to A is also going to have a solution. Clear? So I can write it as AX equals to A and YA equals to A. Let this be equation 3 and this be equation 4, where X and Y are solutions of equations 3 and 4, which implies that X and Y belong to the group G, right? अगर x and y इन दोनों equations के solutions हैं, that means x and y are going to belong to the group only. Now let x equals to E and y equals to f. Now what do these equations form? This is going to be AE equals to A, and let me name this as fifth equation, and FA equals to A. Now let this be the sixth equation, right? हम इतने आ गए that AE is equals to A and FA is equals to A. अब आपको थोड़ा सा visualize हो रहा है that if we are able to prove that E and F are equal, then we can say that there is an identity element which is going to be AE is equals to A, which is equals to EA is equals to A. ये दोनों आपस में equal हैं. That means अगर यहाँ पे AE and FA ये बराबर हो जाए, right? तो हम कह सकते हैं that and if we are able to prove that E and F are equal, that means आपके पास क्या है, एक identity element मिल जाएगा. So exactly that we are trying to do here, right? चलो, now let B belongs to G be any element of, all right. So if B is any element of G, this implies that AX equals to B and YA equals to B will also have solutions, right? So we can name them. How many equations do we have? 5, 6. We can name them 7 and 8. Okay. Now by 7, pay attention in this step. Okay. Now what I'll be doing is I want to get a relation so that I am able to identify the identity element for this group, right? So now for that I will pre-multiply by F and I can write it as FA x equals to FB, right? Now can I substitute the value of FA from here? Where is it? FA. So FA is going to be what? Is equals to A. So this can be written as AX equals to FB, right? This I have taken from equation 6, right? Now AX is what? AX is equals to B only. So can I write B is equals to FB? This is from which equation? 7 equation. From 7, right? Now B is any arbitrary value, right? हमने assume किया that B is any value from G. So can I write it as B equals to E? This will give me the value of B equals to, sorry, E equals to FE, right? Now from or by 8th equation. 8th equation is what? YA equals to B. Now post multiplying by E, I will get YAE equals to BE, right? Now can I substitute the value of AE? AE equals to A from equation 5, right? So I can write it as YA equals to BE, YA equals to BE from 5, right? Now YA is equal to what? B. So this will become B equals to BE. This is from equation 8, right? Now if B can assume any value from G, can I write it as B equals to F? So this will give me F equals to FE. Now combine these two equations. E is equals to FE and F is also equals to FE. So this implies that I can name these equations as 9th and 10th. Okay. This is going to give me that by 9th equation and 10th equation, I will get E equals to F. Now using these two equations, see, AE is equals to A and FA is equals to A, which is 5th and 6th. By 5th and 6th, or I should write by substituting values in equations 5 and 6, I can say that AE equals to EA equals to A. This implies that there exists E belongs to G. E is the identity element, right? So now we have associativity, we have the identity element. Now we just have to prove for the inverse part, right? Now अब ऐसे समझो that equations ax plus b and equations ya equals to b, कौन से equations की बात हो रही है? The equations that we assumed initially, right? So these are the equations, ax is equals to b and ya is equals to b are true for all and they have solutions for all, right? Now this means, can I write that ax equals to e and ya equals to e will also have solutions in G, right? They will have solutions. So let x equals to a1 and y equals to a2 be those solutions in G, right? Now this means that a1 equals to e and a2a equals to e. Clear? Any problem till here? No. Now just अब हमें करना क्या है basically? What do we want to do? If I am able to prove that a1 and a2 are equal, है ना? a1 and a2 are equal, then I will get an equation. Then I will get an equation which will be a1 is equals to a1a is equals to e, which is nothing but the definition of inverse, right? For a1 is going to be the inverse. So from here I just have to prove that a1 and a2 are equal. Clear? Now a1 equals to ea1. Now can I substitute the value of e from this equation? So this can be written as a2 a1. Now a2 a1. So a1 can be substituted from here, right? So this is going to be a2 e, which is nothing but a2. What does this give me? That a1 equals to a2. So this implies that a1 equals to a1a equals to e. So this implies that a1 belongs to G is inverse for a belongs to, right? So since we have the two postulates that were given to us initially in the theorem, and then we have the existence of identity, and then we have unique inverse for each element, so that means our algebraic set which was given to us, algebraic structure, that G along with the binary operation forms a group. Yeah, chalo, moving on. Now we have a note. This is not a theorem, but it is a note that in a semi-group the cancellation laws may hold or they may not hold, right? What is a semi-group? Semi-group is semi-group has closure plus associativity. Okay. Now one example is that let S be the set of all 2 cross 2 matrices with all the elements being integers and binary operations being the usual multiple on S. Can we take examples from this set that is given to us, an example from where the cancellation laws are not going to hold? Let's say A equals to 1 0 0 0. Okay, I'm trying to make or take the values in such a manner where AB is equals to AC, okay, and the AB is equals to AC, that equation is going to come equal, but it won't prove that B is equals to C. Here B and C are going to have different values. So if I use, or if I try to check the left cancellation or the right cancellation law in this setup. So I'm going to get 1 0 0 0. This is the value of A. This is B, right? Then you have A again, and this is 0 0 1. Up see, this is going to give me 0 only, 1 into 0, 0 into 1. Then again, this whole row is, a column is 0, so 0. This is 0, then finally 0, right? Now here, 0, 0, 0 and 0. Even though these are equal, it does not imply that B is equals to C. Why? Because we can clearly see that B and C are two different matrices, right? So it clearly states that if you have a semigroup, then it is not necessary that the cancellation laws will hold in this group, right? In this semigroup. Another example is that n plus is also a semigroup. Why? Because when we talk about closure in n plus, n is what? Set of natural numbers, right? So you add any two natural numbers, you are always going to get a natural number only, right? So closure is satisfied. Then you have associativity. Associativity is also satisfied. Why? Because addition made does not matter, right? But where it fails is the identity. For addition, I need 0, right? But 0 does not belong to natural numbers, right? So 0 does not belong to natural number. That is why n is a semigroup. So n does not form a group under the addition, under the binary operation addition. But A plus C, or I should write A plus B equals to A plus C. If this is there, then most definitely A plus B, I can apply minus A on both sides. So this is going to give me 0 plus B, 0 plus C, so B equals to C. So most definitely, if A plus B is equals to A plus C, then definitely B is going to be equal to C. So we have seen two examples. One was where semigroup, it was a semigroup, but it was not holding the cancellation laws. But in this semigroup, the cancellation laws are holding. So how to know that what is the conclusive thing that when a semigroup is going to hold cancellation laws, right? So for that, we have the next theorem. That is, a finite semigroup G star satisfying the cancellation laws forms a group, right? Chalo. Now we'll take the proof for it. Chalo. It is saying that a finite semigroup, okay? The proof is, let G star be a finite semigroup, right? Let G equals to A1, A1, A2, A3 and till AN. Since it's finite, so there are going to be n elements which we have named them as AN, right? AI. So now let A belongs to G, and I'm forming another set whose elements are going to be A1, A2, A3 and till AAN. Clear? What I've done is, I've taken one element from G only and I have multiplied that A in each of the elements of G. Clear? Now this set S is going to have cardinality, or I should say order of S is going to be less than or equal to n, right? Either it is going to have a maximum of n elements, or it is going to have number of elements less than n. Why? Because it might happen that some of these two, any of these 2 or 3 elements might not be unique, right? They might be similar. Now, how to know that order of S conclusively, what is it going to be? For that, we'll take two elements from the set S, any arbitrary element. Let AAI equals to AAJ be two elements of S which are equal, right? Now, if they are equal, that means AAI equals to AAJ. Now, AI equals to AJ. Why? Left cancellation law. Can I cancel both the A's from the left hand side? Why? Because since it is a finite semigroup, that means it is satisfying, it is a finite semigroup and it is satisfying the cancellation laws. So from here I can say that AI is equals to AJ. So this means all the elements of S are distinct, right? Now if all the elements of S are distinct, this implies that order of S is equal to n, right? And also यहाँ से हम कह सकते हैं that we have taken one element from G and we have multiplied that element to each of the element of G, right? So from here we can say that S is going to be a subset of G, right? Now if I combine these two, that S is a subset of G and the order of S is equals to n, this implies that S is equals to G, right? यहाँ से हमें क्या पता चला? That S is going to be a set in which the elements are of the form AAI. That means AA1, AA2, AA3, A up till AN, right? So if any arbitrary element B, if I take from the set S, it is always going to have a solution, right? Now let B belongs to S, B equals to AAI. It is going to be of the form AAI, right? Where I is going to lie between 1 and n, right? So this means that B has a solution that is AI for all the values of I. This implies that B equals to AX will always have a solution, and that solution is also going to be unique, right? Why? Because all the elements of S are unique only, so all AIs are going to be unique. So now from the theorem that we just did, the previous theorem, this one, which says that if there is a set which satisfies associativity and has these kind of equations which have solutions, then that set is definitely going to form a group, right? So this same theorem we can apply here. So by, or I should first write that similarly YA equals to B will also have unique solution, right? So this implies that by previous theorem, G is a group, right? Associativity कहाँ से आएगी? From where will we get the associative property? It is a semi group. So semi group में क्या होता है? Closure and associativity definitely होती है. That is why we are able to apply the previous theorem, right? चलो, तो now अभी हमने क्या सीखा? That अगर एक semi group है and it is satisfying the cancellation laws, then it definitely forms a group. Clear? चलो. Now the next theorem is the uniqueness of identity. Pretty straightforward, nothing fancy, very simple. that let G star be a group then the identity element is unique. ठीक है? So let's take a proof फटाफट से, very easy proof. कैसे? What do we use here? We use contradiction method, right? So let E1 and E2 be two identities of the group E. So if E1 and E2 both are identities, let us consider E1 as the identity first. If E1 is identity, then E2 E1 equals to E1 E2 equals to E2, right? E1 is identity element, right? So it is going to satisfy E2 E1, that means E2 is some other element of the group, है ना? तो उसके साथ में E1 is going to be satisfying the identity element property. So this means that this is going to be equals to E2, right? Now similarly, if E2 is the identity, E1 E2 equals to E2 E1 equals to E1. Can you see what is happening? For both, from both these equations, I can say that E1 E2 equals to E2 E1 equals to E1 equals to E2, which is nothing but E. So this implies that E1 equals to E is the unique identity element, right? I'm guessing you know already what is the next theorem going to be. It is going to be uniqueness of inverse. Pause this video here and try to solve this question by yourself. Similar method वही करना है आपने, use of contradiction method. आप दो inverses मानो किसी एक element के and try to solve it. Here, let G star be a group and A belongs to G, A inverse, A1 inverse, or we'll take अच्छा, we are writing the theorem abhi na. Then A dash is the unique inverse of A, right? Now proof, very easy, we know how to do it. Let A dash and A double dash be two inverses of A, right? Now since G is a group, so there exists E such that AE equals to EA equals to A, right? So this implies that when A1 is going to be or A dash is going to be inverse, so A dash is equals to A dash A equals to E, right? Also A dash A double dash is equals to A double dash A equals to E. So from here, if I combine these two parts or the first part of the inequation or the equation, I'll get A dash equals to A double dash and A dash A equals to A double dash A. Since it is a group, it is going to satisfy the cancellation laws, right? So applying left cancellation law, I'll get A dash equals to A double dash, right? And here applying right cancellation laws, I will get A is equals to A dash. This implies that A has unique inverse. Clear? Chalo. Moving on. I guess we have two very simple such theorems more, and then we will be winding up this lecture. And uske baad mein we will be taking up laws of exponents, and then afterwards we will be taking finite group. Clear? Now, this theorem is, if the inverse of A is A inverse, then inverse of A inverse is A. That is, A inverse's inverse is going to be A. Very simple to prove. Okay? Let G star be a group, right? This implies that A belongs to G for all A belongs to G. There exists A inverse belongs to G such that A inverse equals to A inverse A equals to, right, is identity element. ठीक है, हमें क्या प्रूव करना है? we want to find out the value of A inverse inverse, right? तो हमारे पास यही इंफॉर्मेशन है जो इनवर्स में हम डील कर रहे हैं, राइट? तो कैन आई यूज दिस पार्ट नाउ? आप कोई सा भी पार्ट यूज कर सकते हो, दैट्स ऑफ नो कॉन्सिक्वेंस. A inverse equals to E. I want to find out the value of A inverse inverse, right? So in order to do that, can I multiply by A inverse inverse on this side, right? यहाँ पे I'll be left with just A inverse inverse, and then I can manipulate whatever is given here to find out the value, right? Which is consequently what we want. I want A here, so I'm going to get A on the left side. So now multiplying by A inverse is inverse on both sides, right? I will have A inverse equals to A inverse inverse, right? Now look closely. Since it is a group, it is going to hold associativity. So if initially I am solving these two together, I can solve these two together as well, right? यहाँ पे, wait a second, it is going to be E A inverse. Clear? Chalo. So now I can write it as A inverse dot A inverse is inverse, right? And here I'll be left with A inverse. Now pay attention. A inverse and A inverse is inverse. So what is it going to be? It is eventually going to be E, right? Why? A inverse and A inverse are inverses of each other. So this is going to be A equals to A inverse, which right from the start we wanted to here. So the value of A inverse is going to be A only. So यहाँ पे you can write hence. Chalo. Next up we have, if G dot is a group, then AB inverse equals to B inverse A inverse. Now let G star be a group let A belongs to G. This implies that A inverse belongs to G, right? Any problem? Now, okay, B belongs to G, or I will write it first as this only. So A inverse equals to A inverse A equals to E, and let B belongs to G. This implies that B inverse belongs to G, such that B inverse equals to B inverse B equals to E, right? Now, let A comma B belongs to G. So this implies that AB belongs to G. Any problem with that? A and B are two separate elements. They are going to belong to G as well. The product of these two is also going to belong to G. And then A inverse and B inverse belong to G. This implies that B inverse, A inverse is going to belong to G, right? Both of these are elements only, doesn't matter the order. उनका जो product है or the operation when applied to both of these elements is going to belong in the group also, right? Now, if I take the product of these two elements, what am I going to get? AB, B inverse, A inverse is going to be, can I solve these two first? So A, B dot B inverse equals to A inverse can be written as AE, A inverse, which is nothing but A inverse equals to E. Now from here, can I say that AB and this part B inverse A inverse are inverses of each other? Why? Because it is giving me identity as the answer. And similarly, if I apply it the other way, then also it is going to give me the same answer. See, B inverse E B is equals to B inverse B, which is nothing but E. So this implies that AB and B inverse A inverse are inverses of each other. So this implies that AB's inverse is equal to B inverse A inverse. Clear? So I guess with this, today we'll be pausing here and we'll be taking up rest of the theorems. I guess laws of exponents is remaining, that we'll be taking, and then we'll be starting groups from there. So that's all for today. Thank you.